Now, my dear children, we will go to the next topic of this chapter, semiconductor electronics or devices. Okay, and the topic that we go now to discuss is types of semiconductor. Now, semiconductor is basically classified on the basis of their conductivity, because conductivity of semiconductor lies between conductor and insulator. Okay, and in the last YouTube video, you saw that the conductivity in semiconductor is basically done by the electrons and the holes, which are the what? Charge carrier. Okay, and even you saw that that when the temperature increases, the conductivity also what? Increases. Okay, but conductivity can be increased even by the addition of some impurities without much increasing the temperature. Even the conductivity can be increased without adding any impurities, but with the rise of the temperature. Okay, so on the basis of that, the semiconductor is classified into two types. So there are two types of what? Semiconductor. One is called intrinsic or pure semiconductor. One is called extrinsic or impure semiconductor. So how many types of semiconductor we have? Two types. One is called intrinsic, which is also known as pure semiconductors, or another is called extrinsic or impure semiconductors. Now let's start with intrinsic or pure semiconductor. Now the word only suggests that the conductor is pure semiconductor. The pure semiconductor means free from any impurity atoms. That's why the statement is written out here. A pure semiconductors free from any impurities means the presence of any other atoms other than this tetravalent element are called intrinsic semiconductor. Because you know, in the last YouTube video you learned that germanium, silicon, even carbon are the semiconductor. Okay, and these elements which actually lies in group 4 of the periodic table, and they have what? Tetravalent element. Okay, but in this semiconductor, if there is no impurities present, there is no any other impurities present and atoms are present, then if this semiconductor are in pure state, then such pure semiconductor are called pure semiconductor. That's why the statement is written, pure semiconductor are the semiconductor free from any impurity. Okay, and this pure semiconductor are also called intrinsic semiconductor, or simply called as pure semiconductor. And generally group 4 elements, as I said, germanium, silicon. Okay, there are other elements also, but we mostly take these two semiconductors as an example of semiconductor. So generally group 4 element, germanium, silicon are used as a what? Pure semiconductor. Used as a what conductor? Semiconductor. Now, to know that why this germanium, silicon act as a pure semiconductor, because silicon, if I take silicon, the atomic number of silicon is 14. So we can write its electronic configuration on the basis of blocks. Okay, so 1s2, 2s2, 2p6, 3s2, 3p2. So if you look at this is the outermost orbit where there are how many electrons present? 4 electrons. So these are the 4 electrons which are also called valence electron. Okay, and if the valence electron is 4, the valence is also 4. That means this silicon has a valency what? 4. Similarly, germanium, whose atomic number is 32, which can also be written in the same way: 1s2, 2s2, 2p6, 3s2, 3p6 and 3d10, and even 4s2 and 4p2. So if you look at this last orbit, where there are how many electrons? 4 electrons. Okay, so these electrons are also called valence electron, so that's why the valence is also 4, which means this silicon and germanium has a valency 4. And if elements having valency 4 means they are also called tetravalent element. Okay, so that means the atom of both germanium and silicon have 4 valence electrons, so that the valence is what? 4. That's why normally pure semiconductor are made with group 4 element, and they are also called tetravalent element. Now we will discuss the mechanism of electrical conduction which can occur in intrinsic semiconductor by taking this silicon and germanium as a pure semiconductor. Okay, now to understand this mechanism of electrical conduction, okay, in intrinsic semiconductor, okay, so we take the atom of germanium of silicon, and you know, atom of both germanium and silicon have how many valence electron in the outermost orbit? 4 valence electrons. That's why they are called tetravalent element. Okay. Now, usually what happens? Each atom, each of the 4 valence electron of an atom, each of the 4 valence electron of the what atom is set by an electron of its nearest neighboring atoms. And when they share the electron, they actually form a bond known as covalent bond, because covalent bond is usually formed by sharing of what electrons. So due to this covalent bond which is so formed between the electron which shared between the neighboring atoms, okay, they provide a force called binding force. They provide a force called what? Binding force. Now to understand this in more details, okay, let me show with the help of diagram. Now if you look at this diagram, so this is the structure, okay, the crystal structure of this silicon and germanium as a pure semiconductor. Because in a crystal structure of silicon or germanium, there are number of what? Silicon or germanium atoms. But every silicon or germanium atom has how many valence electron? 4 valence electron, okay. And this 4 valence electron, any one of the 4 valence electron, they share with the other neighboring valence electron of the neighboring atoms, okay. So that's why if you look at the diagram, this circle with +4 which I have written, this is nothing but the nucleus plus, this is nucleus plus inner electrons of either silicon or what? Germanium. So this is for silicon or what? Germanium, okay. Now the dot part which is shown out here are the valence electron. Now just look at it. If I take this atom of silicon or germanium, this has how many valence electron? 1, 2, 3, 4. So these are the 4 valence electron. These electrons are called what electron? Valence electron. Okay, these are called what electron? Valence electron. Now there is another atom of silicon, okay, with how many valence electron? 4 valence electron. 1, 2, 3, 4 valence electron. Similarly, another atom of silicon or germanium have 4 valence electron. 1, 2, 3, 4. So whatever number of atoms which are there in silicon or germanium, okay, every atom acquire how many valence electron? 4 valence electron. And this electron, valence electron of one atom will share with the valence electron of other atom by forming a bond known as covalent bond. That's why this bond is called covalent bond. So this diagram you can see, this is called covalent bond. Covalent bond. So children, look at the diagram. Between this one valence electron of this atom and one valence electron of this atom, they are sharing each other. So they are sharing each other to form what? Covalent bond. And due to this covalent bond, okay, so formed, provide a binding force between them. They provide a what force? Binding force between them to acquire in the what? Crystal of silicon or germanium. So in this way, so many atoms of silicon germanium can form a covalent bond, okay, by sharing the electron, valence electron with the neighboring atoms. Now suppose if I consider this is the silicon or germanium atom which is at absolute 0. Now just considering that this is our absolute 0. So what happens if the temperature which is say near about absolute 0, all the valence electron are tightly bound, okay, to the what? Nucleus. Tightly bound to the nucleus, okay, and no free electrons are available to conduct electricity through the crystal. That means the covalent bond which is formed, okay, and the electrons, valence electrons which are present in the atoms, okay, are tightly bound, okay, are tightly bound to the core or with the central part of the nucleus, okay. So due to which there is no electrons, no valence electron which can break covalent bond to move to the which band? Conduction band. So when the semiconductor is taken at absolute 0, then the valence band is completely filled because all the electrons are in the which are valence electrons only, and they are simply forming a what bond? Covalent bond. So there will be no electron, single electron which can conduct electricity. Means which can conduct electricity means they single electron can break covalent bond and move to the which band? Conduction band. So children, one thing I want to tell you that when electrical conductivity can take place when any of the valence electron break covalent bond and move to the which band? Conduction band. Okay, but at absolute 0 temperature, say I consider this is at absolute 0 temperature, what happened? There is no valence electron which can break covalent bond and move to the which band? Conduction band. That's why, as I have told you that when semiconductor is taken at absolute 0 temperature, then that semiconductor behaves as ideal insulator. That means they does not conduct electricity at all. That's why at absolute zero temperature, as I said already, all the valence electrons are tightly bound by the nucleus so that no valence electron can break covalent bond, okay, that binding force, and move from valence band to which band? Conduction band. Which means in case of pure semiconductor at absolute zero temperature, the conduction band is completely filled, whereas valence band is completely filled and conduction band is completely empty. But that valence band, electron present in the valence band cannot move from to the which band? Conduction band. Okay, because the binding force between the nucleus and the valence electron are so tight so that covalent bond cannot be break. Okay, so that if covalent bond cannot be break, okay, then what happen? That's pure semiconductor, okay, either silicon or germanium, okay, will behaves as a what? Ideal insulator. Means ideal insulator means which does not conduct electricity at all. Okay, because there is no electron, a single electron that you can find in the conduction band to conduct what? Electricity. Okay, and if there is no movement of electron from valence band to conduction band, definitely there is no hole will create in the valence band. Remember this part. And if there is no holes and no electron present in the conduction band, then definitely conduction cannot be takes place. So that's why semiconductor can behaves as insulator, ideal insulator at absolute zero temperature. But we do the same, we take the same semiconductor now at what temperature? Room temperature. Now we take the same silicon or germanium semiconductor, a pure semiconductor, but at what temperature? Room temperature. Okay, so what temperature? Room temperature. So this is the figure. So figure number 2, which indicate the semiconductor at what temperature? Room temperature. Okay, so what happened at room temperature? Very few of the valence electron, very few of the valence electron are thermally excited, okay, from valence band to the which band? Conduction band. That means very few of the electrons, okay, get some extra energy called thermal energy, okay, and get thermally excited and break covalent bond. Remember this, they break covalent bond to move from valence band to which band? Conduction band. So as soon as one of the valence electron move from valence band to conduction band, what happened? There is a hole which is created. Okay, the hole will create it, and this vacancy which is created in the valence band is called what? Holes. So for that, if you look at the diagram, this is the crystal structure of silicon or germanium. So at room temperature, suppose one of the valence electron present in this end will move from valence band to conduction band, okay, after leaving the covalent bond. So as soon as it goes from valence band to covalent bond, conduction band, then this electron become free, and these electrons are called free electrons. Even you can see the electron from valence band move to the conduction band by breaking covalent bond. So this electron is called what electron? Free electrons. And free electrons are always remain in which band? Conduction band. So this is also called free electrons. So as soon as the electron become free by breaking covalent bond, then there is a vacancy which is created, and this vacancy is called holes. So this is your hole, H-O-L-E, hole. A vacancy which is created in the valence band will be called hole. Similarly, there is a vacancy which is created in the valence band which is called hole. So whatever number of electrons move from valence band to conduction band, that much number of holes will be created in the which band? Valence band. Like example, this is just for the example, you can see there are 2 electrons move from valence band to conduction band by breaking covalent bond. Means how many holes has created? 2 holes. But this number of movement of valence band to conduction band can occur even if you increase the temperature. But remember this, at room temperature, very few of the valence electron get thermally excited, okay, from valence, thermally excited, and they break covalent bond to move from valence band to conduction band. So what happened when the temperature increases? That means higher the temperature, larger the number of electrons move from valence band to conduction band. So which means large number of what? Electron hole pair produces in the semiconductor. Okay. Now when this semiconductor is connected to a cell of battery, when this semiconductor is connected to a cell of battery, means when an electric field is applied to this crystal of semiconductor on that at room temperature, then what happened? The free electrons present in the conduction band, like these are the free electrons present in the conduction band, move in the direction opposite to the field, because electron always move in a direction opposite to the field, electric field, and holes in the valence band See, holes in the valence band also move in the direction to the field. And due to this movement of holes and electron, which give rise to the current, and this current is called electric current. But remember this, in case of pure semiconductor, the current that we obtain by a very few electrons, movement of few electrons in the conduction band, and very few holes, moving in the valence band, very few electrons present in the conduction band, and very few holes present in the valence band conduct electricity, but this electricity will be very, very less. Means this current will be very, very less. That's why children remember this part, that in case of semiconductor, current conduction takes place due to the movement of both electrons and hole. Current conduction takes place due to the movement of both electrons as well as hole. But electron move from which band? Conduction band, and holes move in the which band? Valence band. Okay. Now, as you know, in case of pure semiconductor, whatever number of electrons present in the conduction band, equal number of holes will create it in the valence band. Okay. But the contribution of current, electric current, due to electron present in the conduction band will be larger as compared to the holes. Compared to the holes. This is because the electrons which are free in the conduction band move more easily than the bound electrons in the valence band, which causes the motion of the holes. Now look at it. These electrons are the free electrons. Okay, these electrons are not bound by any of the charged particle. They are free, and they are in the which band? Conduction band. So when they move more easily as compared to the holes which they move in the valence band. So movement of hole will be apparent, not as fast as electrons, because these holes are still bound by the electron, one of the electron present in the neighboring valence band. Okay, that's why, let me tell you this point again. In case of pure semiconductor, although the number of electrons, free electrons in the conduction band is same as number of holes created in the valence band, but the current conduction is mostly contributed due to the movement of holes, movement of electrons in the conduction band. As I said, because the free electrons in the conduction band move more freely or more easily than the electrons, holes move in the valence band, because these holes are even bound by the electrons present in the valence band. Like this hole is bound by this electron in the valence band. Even this hole is bound by these electrons in the valence band. Okay, so this point you keep in mind. So with this condition, so you can even take a note that the conductivity in intrinsic semiconductor is very poor. It's not very large. Okay, because very few of electrons, free electrons and holes move and conduct current. Okay, that means I write down the point, the conductivity, conductivity in an intrinsic. The intrinsic is also called pure semiconductor. Conductivity in intrinsic or pure semiconductor is very poor. Very poor. Unless the temperature is very, very high, and it's not actually done in case of semiconductor. This is the reason that intrinsic semiconductor or pure semiconductor have no practical utility. That means this semiconductor is basically not used for making any instrument or any semiconductor devices and all. Okay, because of poor conductivity, and even if you have to increase the conductivity, you have to increase the temperature to a large extent, which is not possible, because even if you increase the temperature to a large extent to a semiconductor, what happens? That may melt also. The semiconductor device may melt also. Okay, so under this case, the intrinsic semiconductor may not use. It cannot be used for practical purposes. Okay, so this point you need to keep in mind. Now, next thing that we need to see is the concentration. The concentration of these free electrons and hole present in intrinsic semiconductor. Now, basically, concentration of free electrons or free holes in intrinsic semiconductor means the number of free electrons or holes present per unit volume of a semiconductor. So this can also be observed, okay, because when we talk about the semiconductor, pure semiconductor, okay, at room temperature also, we know that if there are 10 electrons present in the conduction band, move from valence band to conduction band, how many holes will create in the valence band? 10 holes only will create in the valence band, which means there are equal number of electrons present in the conduction band and equal number of holes created in the what band? Conduction band. So from this statement only you can understand that the concentration of electrons and hole in semiconductor, pure semiconductor is, or intrinsic semiconductor is exactly equal. So for that, let me just consider that Ne, I am writing Ne and NH. Okay, let me write this way also, NH. E implies electron, H implies hole. And these are the what? These are the concentration. I consider these are the concentration of what? Free electrons. Concentration of free electrons and holes in what? What conductor? Pure semiconductor. In what conductor? Pure semiconductor. So as for the statement which I said, that with this concentration are equal, so I can write now Ne equals to NH. That means both concentration are equal, and both this concentration are also known as Ni. We call by the common name, and this common name is called intrinsic concentration. We also call as intrinsic concentration. Yes, as I said, intrinsic concentration. So remember this point, that in case of pure semiconductor, Ne equals to NH. Both Ne and NH is also called Ni. That is called intrinsic concentration. Now let me just take the example like for germanium. Okay, one of the pure semiconductor, that is GE. So for germanium as a semiconductor, your intrinsic concentration will be approximately how much? 2.4 into 10 to the power 19. 10 to the power what? 19 per meter cube. Look at the amount. So 2.4 into 19 per free electrons or holes, which are called intrinsic concentration, present per unit volume of the volume of what? Volume of this germanium. That means for germanium as a pure semiconductor, how many number of concentration of electrons and hole present per unit volume of a semiconductor? 2.4 into 19 free electrons or hole present per unit volume of semiconductor. Similar we can do for silicon also. So for silicon, your intrinsic concentration value will be how much? 1.5 into 10 to the power 16 per meter cube. And these two, you can see this concentration value is basically at what temperature? Room temperature. Room temperature means 27 degrees Celsius, or we can also write at 300 Kelvin. So these two value, that is the intrinsic concentration of germanium and silicon, or is usually measured at what temperature? Room temperature. So this is the detailed explanation of pure or intrinsic semiconductor. Now from here you can understood that, okay, pure intrinsic semiconductor has equal number of electrons in the conduction band and equal number of holes in the valence band. The conductivity is very less. Okay, the conductivity can be increased, okay, by increasing the temperature. Okay, and this conductivity, due to less conductivity or poor conductivity, this intrinsic semiconductor or pure semiconductor cannot be used for practical purposes. Now, in order to use the semiconductor for practical purposes without increasing the temperature, to increase the conductivity to a large extent, we can increase by adding some impurity atom to the pure semiconductor, and that actually is called impure or extrinsic semiconductor. And children, the details of extrinsic or impure semiconductor you will be learning in the next YouTube video.